This is Chapter 10 in Astronomy 100, Other Planetary Systems, the New Science of Distant Worlds. And it really is a new science. Since about 1995, when we first discovered what we thought was an extrasolar planet, we've been discovering hundreds, even thousands more planets with varying degrees of success and with different methods. So in 10.1, we're going to be looking at detecting planets around other stars. So how do we find them? Section 10.2 is about the nature of planets around other stars. And then 10.3 talks about the formation of other planetary systems. So let's look at 10.1 first. How do we detect planets around other stars? Well, the same picture is on page 261 of your textbook. It shows planets actually orbiting a star. This is direct observation, and this would be something which is very rare. Obviously, being able to watch a single star and the planets going around it, or over a period of months or years, seeing that there's movement of these planets around the star is very, very unusual. So this would be one way to find another solar system, but very, very difficult. Oh, plus also notice the view that we have. It's a top-down view. If the planets are orbiting at some kind of an angle or edge on to us, we're not going to be able to see this movement of planets like we do in this picture. So why are extrasolar planets difficult to detect? Well, a sun-like star is about 1 billion times brighter than the light reflected from its planets. Planets are very, very dim. The only way we can see them is from reflected light. Planets are close to their stars relative to the distance from us to the star. So it's kind of like being in San Francisco and trying to see a pinhead 15 meters from a grapefruit in Washington, D.C. That's the relative difficulty we would have in finding a planet orbiting another star. So there's actually two ways to detect planets. One is direct, where we have pictures or spectra of the planets themselves, and the other is indirect, which is much more numerous. We can measure the stellar properties and reveal the effects of the orbiting planets going around it. Here's one way we might be able to detect a planet orbiting a star, and we use the Sun and Jupiter as an example here. The Sun orbits, or I should say Jupiter orbits the Sun, but in some respect the Sun orbits Jupiter. They have very large gravitational attractions to each other. So as Jupiter orbits the Sun is actually pulled toward Jupiter, kind of giving it a wobble. Now take all of the planets. The Sun's motion around the solar system's center of mass depends on the tug from all those other planets, including Earth. So astronomers have measured this motion and determined the masses and orbits of other planets doing the same thing. It's called the astrometric technique. We can detect planets by measuring the change in a star's position in the sky. However, the motions are very, very small and very difficult to measure. And of course, the farther out you go, the harder it is to measure that movement. Here's another technique. It's called the Doppler technique. We already know what the Doppler effect is. We know that as something is approaching us, light will be blue shifted, and as an object is moving away from us, light is red shifted. Well, we can detect changes in the speed of an object revolving around another object with a measurement as small as 1 meter per second, which is pretty incredible. Here's the first extrasolar planet that was measured in 1995. The Doppler shift of this star indirectly revealed a planet with a 4-day orbital period. This was with the Doppler shift. The short period means that the planet has a very small orbital distance, very close to the star. So this was the first one to be discovered. Transits and eclipses. Here's another way we can measure or find planets orbiting a star. A transit is when a planet crosses in front of a star. It reduces the apparent brightness and tells us the planet's radius. the planet is not giving off any light. Instead, it's darkening or giving us less light from that star. So we're going to see a dip in the light curve of that star. And apparently that can give us some information. Knowing what the star's brightness is initially, and seeing that the planet darkens it just a little bit, that star light being blocked gives us some kind of a clue as to the radius of the planet. Sometimes an eclipse will occur. The planet passes behind the star, and that can also be detected. This is the spacecraft that's been doing so much for us since 2008, looking for transiting planets. It's designed to measure very, very small drops in brightness when a planet passes or eclipses a sun-like star. There are other ways. Gravitational lensing, where mass will bend light in a special way when a star passes in front of another star. And there's even things called dust disks, where a gap or a wave or a ripple in dusty gas around a star can indicate the presence of a planet or planets. So how do we detect planets around other stars? Well, direct sunlight, or starlight, is billions of times brighter than the starlight reflected from the planets, so it makes imaging pretty tough. But we also have a star's periodic motion detected through Doppler shift, or by measuring its motion across the sky. And finally, transiting planets periodically reduce a star's brightness. So if we can measure that reduction in brightness, we can get more information about the star. So what's the nature of planets around other stars? What properties of extrasolar planets can we measure? And how do extrasolar planets compare with planets in our own solar system? Well, here's two different curves of the same type of planet. For transiting planets, the Doppler method gives us an accurate mass. The transit method will also yield the radius of the planet. So if we have the mass and we have the volume of the planet, we can calculate the planet's density. Here are some other measurable properties. The orbital period, of course, the distance from the star, possibly the shape of the planet's mass, its size, its density, and even atmospheric properties in some cases, where if the planet has an atmosphere, as it's passing in front of the star, there might be some sort of a spectrum revealing the components of the atmosphere. What about planet mass and orbit tilt? Well, we can't measure an exact mass for a planet without knowing the tilt of its orbit, because Doppler shift tells us only the velocity toward or away from us. It doesn't tell us the angle. And Doppler data gives us lower limits on masses. Masses could be much higher, again, depending on that angle we're making the observation. Here's a planet, the Kepler-11 system, actually multiple planets in the Kepler-11 system. By looking at the transit data, we can see that there are planets of varying sizes moving around this particular star, and it's all been done with the transit method. So how do extrasolar planets compare with planets in our solar system? Well, the orbits of extrasolar planets are kind of interesting because most of them have orbits smaller than Jupiter. The planets at greater distances are hard to detect because with current techniques. They're just so far away from the star that, for example, we don't have reflected light from it, or the orbital distance is so great that the orbital period is so large. And some orbits of extrasolar planets are much more elongated. They have a higher eccentricity than those in our solar system. So we do have some problems in finding all the planets around all the stars. Here's an interesting diagram. This shows over on the left the planetary radius compared to our solar system, and down along the bottom the orbital period in days of planets we've so far discovered. This is the same diagram that's on page 273. What's interesting is is the grouping of planets on this diagram. It appears that most of the orbital periods are somewhere between 1 and 100 days, not like Earth, which is 365 days. And the planetary radius varies somewhere between 1 and 4 times that of Earth's. So Earth is certainly not unique in that respect. There are probably a lot of other planets out there with similar characteristics, but up until the point this diagram was made, the orbital periods were much, much shorter. So results from Kepler indicate that planets are common, and small planets greatly outnumber the larger planets, as you can see from the graph. The percentage of stars with at least one planet is increasing as you go from the bottom to the top, and then the actual size of the planet is going from left to right. So super Earths or mini Neptunes are apparently the more dominant form of planet size. This is probably the heart of Chapter 10, showing the masses and sizes of extrasolar planets. Over on the left, you see the planets in our solar system, with arrows pointing down to where they would be on this diagram. So what we're looking at here is a plot of many, many planets, but in respect to our solar system, there are many more planets that are up and to the right compared to our planets, which are the green dots. So we're seeing that apparently a lot of planets that we've so far discovered, on the average, have a higher radius, in other words, a larger size, and have a higher temperature than many of the planets in our solar system. So our solar system isn't unique in the respect that we're the only ones who have this configuration, but it certainly is not as common as what we've seen so far in discovering extrasolar planets. So some extrasolar planets have highly elliptical orbits. We really don't have that in our solar system. Planets show a huge diversity in size and density. And some massive planets called hot Jupiters orbit very close to their stars. In other words, it would be a very large planet, but also very, very close in to the star it orbits, not like our solar system. So what properties of extrasolar planets can we measure? Well, we can measure their orbital properties, such as period, distance, and even shape. The planetary properties, such as the mass and the size of the planet. And possibly extra atmospheric properties, such as temperature and composition, if there is an atmosphere. Planets have a wide variety of masses and sizes, as we see on page 274. And many of those planets are orbiting close to their stars with larger masses than we have in our solar system. So 10.3 has to deal with the formation of other planetary systems. Our goals are, do we need to modify our theory of solar system formation? And are planetary systems like ours common? Those are two very good questions because this science is so new. We really don't have firm answers to these questions. We have many, many more planets to discover and probably more exploration of how everything possibly happened. So here's an example of how we might have to modify our theory. This is on page 276, figure 1013. It shows that some orbiting planets may actually have nudged gas and particles in the disk as it was forming. It caused material to bunch up, and then these regions in turn tugged on the planet, causing it to migrate inward. So what we're looking at here is a possible explanation for why our observations show so many hot Jupiters. So what about revisiting the nebular theory? Well, it predicts that massive Jupiter-like planets should not form inside the frost line, but The discovery of these hot Jupiters inside the frost line have forced a re-examination of the nebular theory. Perhaps we need to modify it a little bit to fit what our observations are actually showing us. So planetary migration or gravitational encounters might explain hot Jupiters. Remember, these are the two factors: planetary migration or gravitational encounters. Those are the two ways that we might explain hot Jupiters. Here's a young planet's motion creating waves in a planet-forming disk. And this model and others could show that matter in these waves tug on a planet, causing its orbit to migrate inward. So it's possible that in the process of the planets forming around the star at the beginning of the solar system's life, that this happened, and because it happened, the planet actually moved inward in its orbit. What about gravitational encounters? Well, a close gravitational encounter between two bigger planets can actually eject one planet while flinging the other one into a highly elliptical orbit. So the common gravitational attraction of two planets can actually throw themselves off quite a bit and change their orbits radically. Multiple close encounters with smaller chunks of planet could also cause inward migration. So that might be an explanation for how some of these larger planets are closer to the star. Planetary types. There seems to be a much greater variety of planet types than we find in our solar system. This includes gas giants with very different densities and possibly water worlds. So there are other types of planets in existence based on our observations so far. So what about modifying the nebular theory? Well, observations of extrasolar planets have shown that the nebular theory is incomplete, and effects like planetary migration and gravitational encounters might be more important than previously thought, at least for other solar systems. For our solar system, not so important. But again, seeing these hot Jupiters so close to the star it orbits gives people some reason to think that there might be something else happening elsewhere in other solar systems. So are planetary systems like ours common? Well, take a look at Earth. As the caption says, the daytime side shows water, it shows land, it shows clouds. It doesn't show civilization. It doesn't show intelligent life. But look at the nighttime side and you see lights. You see places where humans have been able to illuminate the night sky, and that's what you see in those yellowish speckles. That would be an indication that life exists on this planet. So what have we learned? Well, do we need to modify our theory of solar system formation? The original nebular theory can't account for the existence of hot Jupiters, at least not yet. And again, planetary migration or gravitational encounters might explain how Jupiter-like planets moved inward. So, are planetary systems like ours common? We don't know. We just don't know. We have to make observations of many, many more planets, many more solar systems out there, with maybe even more direct observations of planets with better telescopes.